This is the screencast for section 6.5, example 1, logistic growth. So in the last section we looked at exponential growth. You'll explore that in exploration 1. So now we're going to look at logistic growth. Now we have a few tricks we need to learn first before we really dive into the calculus part of the logistic growth. So let's take a look at example 1. First of all, a partial fraction decomposition with distinct linear denominators is a key tool to be used in the logistic growth piece of calculus. Now what this says, if f of x is a rational function where the numerator and denominator are polynomials with the degree of the numerator less than the degree of the denominator, and the denominator can be written as a product of distinct linear factors, so in other words it's factorable, then f of x can be written as a sum of rational functions with distinct linear denominators. So let's see what that means. In example 1, we have a rational function where the denominator can be factored into 2x minus 1 times x minus 3, which then means that since the degree in the denominator is 2 and the degree in the numerator is only 1, I can create a common denominator and use partial fraction decomposition. There's going to be some constant over 2x minus 1 plus some constant over x minus 3 that will equal this rational function of polynomials. So let's find a common denominator. I'm going to multiply a over 2x minus 1 by the x minus 3 over itself, and then b over x minus 3 by the 2x minus 1 over itself, which means then that a times x minus 3 plus b times 2x minus 1 all over our factored trinomial will equal the original expression. It's just a new way of writing it. So kind of in conclusion here, the new numerator, this new constant times x minus 3 plus constant times 2x minus 1 will equal x minus 13. It's just a different way of writing it because we can do this partial fraction decomposition. So now we need to pick values of x that will help us solve for a and b in this situation. So if x equals 3, that means that a would be multiplied by 0, guess why I picked 3, and then b would be multiplied by 5, and that would be, if you add them, that will equal then negative 10. Again, plugging in 3 for each of those x's, which then lets me solve for b, which would be negative 2. Now what about if x were 1/2? That's right, I picked 1/2 because that makes the other binomial 0. Well then a would be multiplied by negative 2.5, b would be multiplied by 0, and their sum would equal negative 12.5 this time, which means a would equal 5. So now I've solved for b and solved for a using specific values of x that let me do that, and then I get that f of x equals x minus 13 over my trinomial. So the original function can be rewritten as 5 over 2x minus 1, the a value over 2x minus 1, minus 2 over x minus 3, so the b value over the x minus 3. So if you graphed the original f of x and the new f of x, they would be the same graph. Now the now try problem number 3 kind of already gave us the initial setup because it told us that the rational function can equal a over x minus 2 plus b over x plus 5. So they already gave you the factored denominator and then the two constants. So all we need to do then is set up the expression to help us solve for a and b with a common denominator. So that means 16 minus x on the left side would equal a times x plus 5 after finding that common denominator, and then plus b times x minus 2, again after finding the common denominator of this rational function, or combining it into one rational function. So now we're going to pick values for x to help solve for a and b. I'm going to pick if x equals negative 5 first, then that means the left side of the equal sign would be 21 equals a times 0, and then plus b times negative 7. So b is negative 3. Then what if x equals 2? Well, that means 14 on the left side, a times equals a times 7 plus b times 0, which means a equals 2. So now I've got my constant for a and my constant for b. So if I plug all that back in, I get that 16 minus x over x squared plus 3x minus 10 does equal 2 over x minus 2 minus 3 over x plus 5. And if you want to see that worked out, here's how that would look. If we started with these two expressions and said prove that they were equal, I could find a common denominator, distribute the numerator, start combining like terms, and then finally my last simplification would show that the format of a over x minus 2 minus b over x plus 5 does in fact equal the original multiplied out with a common denominator format.